The recent reveal of the open software Leap 71 was definitely intriguing because it showed that complex models can now be designed in computational software. Every module of the build includes a set of parameters and rules that can be easily fine-tuned. Combined with simulated fluid dynamics, you can create something that is very complex that was never perceived before. However, the key to all of this is actually building a real workable object. Turbines are arguably one of the most difficult variants to tackle on. A lightweight 10,000 pounds of force turbofan can still fetch into the hundreds of thousands of dollars, with the very large jet engines reaching into the millions. So if you can come up with an in-house manufacturing process, then you can drastically reduce the cost of the engine and the overall aircraft. However, the turbine can also be used as a power generation unit. The current electric VTOL, even with tilt rotors or morphable wings, can only achieve about a 1-hour flight time, or roughly 150 miles with electric motors. The only physical way to bypass this limitation is through a turbogenerator, which keeps the batteries charged. If balanced correctly, the vehicle's range can be significantly increased. This is purely due to the energy density of fuel, which is around 12,000 watt-hours per kilogram, where a battery is around 450, and through this a microturbine can produce up to 300 kilowatts of power. For a little bit of a comparison, a 5cm micro variant can produce over 300 watts for a drone. So there are a lot of potential applications if you can produce a microturbine at a cheap cost. Luckily, Technicon revealed some very interesting developments over the years in microturbine technology. For one, they developed a porous membrane combustor. The porosity of the structure forces the flow radially inward, and this allows for a higher efficiency with the fuel-air mixture. This is one of many examples that can be done with computational engineering, but actually be produced now through additive manufacturing. The same company also revealed an 8-pound or 4-kilogram variant. A typical microturbine build would hold up to 33 parts, but this was consolidated into one monolithic 3D printed part. Bearing seals and cooling channels were all incorporated within. It took roughly 13 hours from an EOS laser powdered fusion printer. But what makes this unique is that Inconel was used, which has a very high strength and heat resistant property. So we are starting to see microturbines emerge into the market. And it's only going to be a matter of time until we see this fully implemented into the field. But what about larger jet engines? Can we actually 3D print an entire turbofan? The Orpheus project was a huge collaboration undertaken by 30 companies, and it combined model-based engineering with AM. A twin-spool prototype was designed and produced in half the amount of time. But like the microturbine, the combustor was tweaked to actually improve the specific fuel consumption, meaning that the overall volume of the engine was reduced. Rolls-Royce, the leader of the project, has stated that a second variant is already being tested, and the end result is to produce something that has a level of scalability, yet produced in half the time and cost when compared to a conventional jet engine. Another type of jet engine has also been 3D printed by a smaller company titled Beehive. Their turbojet is a little bit different from your turbofan in the sense that it has less parts and a little bit less efficient by not having a large bypass area, but it can produce adequate performance for high-speed applications. The company claims that it can be built at 50% of the cost, and this would make sense because the Beech AT500 was built entirely in-house, without outsourcing any of the components. As a demonstrator, will set the stage for engines which can range from 250 to 1,000 pounds of force. What makes this all interesting is that computational fluid dynamics and engineering is already increasing the efficiency and reducing the volume of the typical jet engine. And finally, we're starting to see additive manufacturing catch up and build these complex components. So there are some very interesting developments that happened recently. For one, we're starting to see microturbines being able to be scaled down along with being affordable. And that's a really game changer because now you can have something with a hybrid system that would be able to charge the batteries. And just purely because of the energy density of jet fuel, you would be able to have something that has way more range than a typical pure electric craft. Another thing too is that we're starting to see real jet engines work with AM techniques, and this is the first year where we're starting to see that. Now before we did see other engines that were produced with AM, but they were just prototypes and they never worked. And that's what's so fascinating about the Beehive variant. It still has to be implemented in the field, but one thing's for sure, we're starting to see great strides when it comes to AM manufacturing techniques. It might even be the go-to method in the future for turbines. But more importantly, I would like to know what you think about all this, so please leave a comment, like the video if you enjoyed it, and also make sure to subscribe to my channel.